Good morning, my dear students. Today we'll be discussing about the basic concepts in organic chemistry. Let us talk about the chemical reaction. Chemical reaction. What do you mean by chemical reaction? Let me consider a chemical bond between two elements, and let me consider another reagent, that is CD. Now, when they react, in fact, they are called reactants. First of all, the bond is cleaved. So the cleavage of old bond and formation of a new bond is called chemical reaction. So this A can combine with C and B can combine with D. So this can be called product, and this is a major product means, and this one will be the byproducts. So the cleavage of old bond and formation of a new chemical bond, cleavage of old chemical bond to form a new chemical bond and chemical compound is called chemical reaction. Let us consider substrate. With which we are going to add some reagent, so that sometimes it will form an intermediate that is represented by square bracket. So intermediate, and this is also called transition state. Transition state, that is in between state, and finally it results a product. This is the simplest representation of an organic reaction. The substrate is an organic molecule that undergoes chemical change by adding some reagent. It may pass through an intermediate that is not stable, and finally it results some product. So many chemical reactions are depicted in one or more steps. Then you should know something about the reaction mechanism. Reaction mechanism. Mechanism is a theoretical pathway that describes the changes are occurring in each step during the course of the chemical reaction or chemical change. So we can understand the reaction by following the direction of flow of electrons and the type of intermediate formed during the course of the reaction. Usually the direction of flow of electron can be represented by an arrow like this. So the movement of pair of electron is represented by, that is, this kind of arrow. Double hooked arrow, you can say. A movement of a single electron can be represented by a single hooked arrow like this. So it is pretty clear that for a chemical reaction to occur, there is an electron transfer. There is an electron transfer, and there is a fission of bond, that is cleavage of bond. So this fission of bond or chemical bond or cleavage of bond can be represented in two ways: homolytic cleavage, homolytic, heterolytic. Homo means same. They result the same entities. That is symmetrical splitting. So homolytic cleavage means symmetric splitting. Hetero means different. So this results in heterolytic cleavage, that is unsymmetrical. So unsymmetrical splitting. For example, let me consider chlorine, chlorine. For a bond, minimum 2 electrons are required. In this case, there is an symmetric cleavage. That is, they result in similar entities and they are called chlorine with odd electron and another chlorine with the odd electron. They are called free radicals. Free radical means an atom with odd electron. They are highly energized. And in the case of NaCl, let me say, there arises the heterolytic cleavage. So here, an uneven cleavage, unsymmetric cleavage. So that results Na plus. So one element loses an electron, another element gains an electron. In this case, the ions are the products of what? Heterolysis. So this is called positive ion, that is cation, and negative ion is called anion. So we call this as cation, and this one is anion. Now, let me explain about the transfer of electron, how they take place. Let me consider a molecule like that is C, CH3, 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 and this is bromine. So this undergoes a hydrolysis, H2O. Okay. Now we can represent this by, that is, the electron transfer can take place in this way. Okay. So the bond between C and Br is shifted towards bromine, and that is why the bromine attains a partial negative charge, and carbon in this alkyl group loses an electron, so it is represented by delta plus. So this results carbonium ion, that is CH3, CH3C, CH3. Now it has lost, and this delta plus indicates the partial ionic character. Now it has become the cation, and then Br minus the anion. So this carbon with its positive ion can be called carbocation. This is also known as carbonium ion. It means carbon with positive charge. And this is bromide anion. Do you understand? Bromide anion. Next, now let me talk about the shape of the carbocation. Let me consider C with plus charge, and you have another H here, H here. Then this is below the plane of the paper, and that is indicated by a dotted line. So H. So this is CH3 plus. Actually, this plus is for carbon. So this is the carbocation, and this bond is sp2 s overlap. So, and this is the p orbital. You can represent the orbital like this. It is a dumbbell shaped one. Okay, and this represents the mtp orbital. Mtp orbital. How this mtp orbital arises? Let me explain based on the electronic configuration. Electronic configuration of carbon, and its atomic number is 6. So 1s2, 2s2, 2p2. Let us represent this by a box model. 1s2 and 2s2, and then p orbital will have three modes of orbital, that is px, py, pz. So 1, 2. Do you understand this? So here this is sp2, and for hydrogen it is 1. So simply you can write 1s1. So this is the sp2 s overlap. We can say this is sp2 s overlap. This one is sp2 sp2 overlap. Okay, so this is the shape of carbocation, that is CH3 plus carbocation. Are you able to follow? So actually, when carbon is alone, it will have this configuration, that is 1s2, 2s2, 2p2. But by looking at these hydrogen, they get excited, and probably this hydrogen may jump over to this place. Okay, and this can combine with the three hydrogen atom so that they can be loaded, and there is one more hydrogen atom that is left over, and that is why you are able to get the plus charge here, and that indicates the empty p orbital. So this is the shape of the carbonium cation, and this is also called the carbocation. Now let us explore the shape of carb anion. Shape of carb anion. Carbanion means carbon with the negative charge. So this is C, and you have H here, and this is called the sp3 s overlap, because this carbon involves in sp3 hybridization, and this hydrogen has s. So this is sp3s hybridization. And now you have hydrogen. One hydrogen is on the plane of the paper, another hydrogen which is represented by a bonding with a triangular pattern. So this indicates this CH bond is above the plane of the paper. And then this one is below the plane of the paper, and that is indicated by hydrogen. So H. And now you have an additional lone pair of electrons here. Okay, this is called non-bonding electron. This is not involved in bonding, so that is why it's called non-bonding. Non-bonding sp3 orbital. So this is called non-bonding, and this non-bonding can also be called, that is, lone pair. Lone pair. So its structure can be simply represented by this CH3 with a lone pair. And already you got already 3 hydrogen plus 2 electrons, that is a lone pair. So totally 5 electron. But carbon should have 4 electron only, and there is an excess of what? 1 electron. And that is indicated by minus here, and that is why carb anion. So this is the valency of carbon, that is 4 electron. But in CH3 minus you have additional electron, and that is why this electron represents the negative charge. So this is the way you had to draw this diagram. And then we were talking about the radical. Take down shape of carbon radical. So carbon radical means, for example, CH3 bond CH3. As I already mentioned, if there is a homolysis, it results a free radical. 2 free radicals. This is electron, this is another electron. So this splits into CH3, and free radical is represented by a dot. So CH3, a dot, means they are free radical. So how to represent this free radical? Let us draw this. C, in a similar way, this is on the plane of the paper, CH, and then this is above the plane of the paper, and this is below the plane of the paper. So CH3, it is a trigonal type, and you got the p orbital like this, where you have an unpaired electron. So this is the unpaired electron. This is the unpaired electron in p orbital. This is the unpaired electron in p orbital. So what about this one? This is s orbital, and this is sp2 orbital. So this is called sp2 s overlap. This bond is sp2 s overlap. So this is represented as CH3 dot simply. Okay, you can simply put dot. So this is the shape of carbon radical. Okay. To understand the reaction mechanism of organic chemistry, you should be aware of all these fundamental concepts. So once you are thorough in organic reaction mechanisms, it will be very easy for you to study any type of chemical reactions and you can easily solve the organic chemistry problems. Now let us talk about the relative stability of alkyl carbocations and carboanions. So here the relative stability. Relative stability of carbocation, and here we'll discuss carboanion. We know something about primary, secondary, tertiary. Let me explain that. Let me consider a butane group or butane, CH3, N-butane, CH3. Buta means 4 carbon atom. So how you have to establish the structure? Just look at the root word. That is the prefix. But means 4 carbon chain. Ane means they contain only single bond. So you can draw the structure like this. C, 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 C. I have drawn 4 carbon atoms attached with the 3 bonds like this. And they are it is a normal chain. And then next thing, you have to fill up with the valency of carbon. That is, they are going to combine, each carbon will combine with the hydrogen, but they should have the tetravalency, that is 4 valency. That is, it should be having 4 bonds around each carbon. So it has got already one bond, another bond, another bond, another bond. Finished. So 1, 2, 3, 4. What about this? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Now we can fill up with the hydrogen. So this is the easy way of writing the structure of any organic compound. Then you can establish this is CH3. So you can write simply CH3, and this one CH2, and this one CH2, and this is CH3. But as you expected, it won't be looking linear like this. It will have a tetrahedral structure, so it will be zigzag. So you can start like this: CH3 bond, CH2 bond, CH2 bond, CH3. Again, now actually this C, it is surrounded by hydrogen. So it is the tetrahedral hydrogen. So you can put hydrogen, 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 bond, C, hydrogen, hydrogen, and C, hydrogen, hydrogen, and C, that is hydrogen, hydrogen, hydrogen. So this is the way it can be further illustrated. So CH3, CH2, CH2, CH3. Then again you can draw by bond line representation also. So instead of CH3, you can put a dot, CH2 link, another CH2 link, another CH3. So the terminal is CH3. So in order to represent this, you can put hydrogen, 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 and this one is hydrogen, hydrogen, and this one hydrogen, hydrogen, and this one is hydrogen, 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 3 hydrogen. So where you have at each corner, each edge, you have carbon, 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 carbon. And this is further simplified as If you write like this, it is understood this is CH3, CH2, CH2, CH3. Okay. So this is N-butane. Then we will draw the structure of isobutane. That is the secondary butane. Isobutane. Now, isobutane means similarly branched, CC. And then you have to add another C, right? Now, this is isobutane. You have to fill up with hydrogen. So, 1 CH3, 4, 1 CH3, 4, 1 bond, so CH3, 4. Is it not? So 4, each carbon has got 4. And what about this? You can put hydrogen only. So how to represent this by a simple bond line? You can simply represent like this. So this represents isobutane. Let us have another structure, isopentane. So isopentane means you can have a even branch like this, symmetric branch. So already 3, and then 4, then 5, because penta means 5 carbon atom. So I accounted for 5 carbon atom. Now substitute with this is already 1, so 3 hydrogen. This is 1, so 3 hydrogen. 1, 2, 3, so you can put only 1 hydrogen. 1, 2, you can put 2 hydrogen. Ensure each carbon has 4 valencies, that is 4 bonds. And what about this? The terminal. So being terminal, it is CH3. How to represent by bond line formula? CH, CH3, CH, CH3, and you can put CH2, CH3. That's all. So CH3, CH3, this is CH, this is CH2, this is CH3. So this is the easy way of what? Drawing the structures of organic compound. Okay. Then again, let us consider tertiary pentane. This is secondary butane, secondary pentane. Now I am talking about tertiary pentane. What about this tertiary pentane? It is branched thrice. So C, 1, 2, 3. C, C, C. And then again 1, 2, 3, 4. Then you can put fifth carbon atom here. Right? Now this is CH3, 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 CH3. Such type of structure can be elaborated like this. That is, it is surrounded by 4CH3 like this. Is it not? So it is also known as neopentane. Neopentane. Penta means 5. And this is a tertiary pentane because it is in the tertiary manner. Okay, the C is connected to 3 branches. Okay, now let me have some halide also, and this can be explained in this way. Tertiary pentyl chloride. Let us discuss this. So tertiary means 1, 2, 3. Tertiary. Pentyl means 5 carbon atoms. So 1, 2, 3, 4, and you have 5. Chloride, you can put simply chloride. That's all. So you can fill up with hydrogen. CH3, 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 CH2. So this is called tertiary butentyl chloride. Got this? And this is also called neopentyl chloride. Okay. Now all these things can be simply represented. For example, you got 1, 2, 3. So CH thrice. Okay. and C is here, then you can put CH2Cl. So in this way, this can be represented very easily. It means there are three methyl group around this carbon. The remaining is attached to CH2Cl like this. Okay. Now let me talk about the different types of carbocations. That is primary, secondary, tertiary. So this is the primary cation CH3 plus, primary carbocation CH3 plus, secondary carbocation means it should be branched, is it not? So it can be CH3 twice, CH, okay, you can put plus here. So this is called secondary carbocation. Tertiary carbocation can be represented like this: C, CH3, CH3, CH3. Now plus. So this is called tertiary carbocation. 3 degree carbo. 3 degree means tertiary carbocation. And this is also represented in this way, that is CH3 twice. Okay, CH3 twice, and you can put CH, then plus. And how to represent this? CH3 thrice and with single C plus. So this represents the carbocation tertiary type. Now we are going to explain the relative stability of these different types of cation. So in fact, the tertiary group like this CH3 thrice is more stable than CH3 twice, and that is more stable than CH2 CH3 plus, that is primary, and if it has single, and that is further greater than CH3 plus. So this is the way you should understand. It means the highest is this, the lowest is this. So the stability wise, so when it is a more, I mean, surrounded by more methyl group, that is tertiary type, that is the most stable carbocation. Okay. Similarly, carboanion. In the case of carboanion also, C minus with the CH3 thrice will be more stable. That is tertiary. And I'm sorry, that is less stable. This is just the opposite. So you can put less than. And then CH minus, this is secondary. CH3 twice, that is less stable than CH2 minus CH3 primary, and that is less stable than CH3 minus. Okay. So you had to be thorough with this. You had to buy heart. As far as carbocation is concerned, which is the most stable ion? Tertiary ion is the most stable one. Okay, this is tertiary. And as far as the carboanion is concerned, CH3 minus is the most stable. Okay, and this is 1 degree, this is 2 degree, this is 3 degree. This is just opposite. You remember one thing, and if it is anion, it is reversed. In that way, you can remember. Okay. Now let us explain about the nucleophiles and electrophiles. Take that. Let me start with nucleophiles. Nucleo means plus, phile means attract. So they are called nucleophilic reagents. Nucleophilic reagents. That is, reagent means an attacking species. So it goes in search of positive center. So reagents go in search of positive center. Positive center means this is carbocation, that is carbonium ion. And here reagents that should go in search of positive center means it should have a minus charge. So it can be a negatively charged reagent or electron rich group. Electron rich group. Electron rich group. So what are nucleophilic reagents? Nucleophilic reagents are negative and they are electron rich. They go in search of positive center because phile means to attract, to love, to go in search of. So to attract. So which can attract the positive center? Only the negative. So nucleo, N-U-C-L-E, nucleophile. Okay. Now let me explain different types of nucleophiles. So they are all electron rich, they are negative. This nucleophile can be classified into two types. Take down. Nucleophiles can be classified into two types. One is, that is, negatively charged species or nucleophile. Another is, that is, they are neutral molecule but they are electron rich. So electron rich neutral molecules. It need not be negative, but it can be electron rich. So it can be neutral molecule. Likewise, we can classify it into two. Why they are electron rich? Because they have some unshared, that is non-bonding electron. They have unshared pair of electrons. Example, we have nitrogen with a lone pair, oxygen with the two lone pairs, sulfur with the two lone pairs, and a negatively charged, that is halides. You can simply represent by X minus. So this can be Cl minus, Br minus, okay, iodide minus. And you can have some carboxylate ions also, hydroxyl ion. So this is called OH minus ion. What do you call it? Hydroxyl ion. Write down hydroxyl ion. Then you have, this is called alkoxide anion, ORO minus. What do you call it? Alkoxide. This is alkyl group. This is oxide. So alkoxide. Okay. You had to remember all these things. Alkoxide. What do you call this? Hydroxyl. Hydroxyl group, alkoxide group. Then you have carboxylate anion or COO minus. This is called carboxylate anion. So carboxylate group. So this nitrogen is present in ammonia and amine as NH3 and then amine or NH2. And this oxygen is present in water, then alcohol ROH and ether ROR, and sulfur may be present in thiol. If you put all ROH, it is called alcohol. When you replace oxygen by sulfur, it is called thioalcohol, simply called thiol. So R instead of O, you can put S, then H. What do you call this compound? Thiol. Right? Now, let me illustrate all these structures so that you can have a better knowledge. You must always have some basic idea about the Lewis structure. So let me take up the very simple one, nitrogen. Okay. I was talking about the electron rich neutral molecule, means they have unshared pair of electron, that is non-bonding electron, that is what? Lone pair of electrons. So what are the different terms I have used? One is unshared pair of electron, and that is also called a non-bonding electron, and that is also called lone pair of electrons. So all these things can be explained based on the electronic configuration only. Let me talk about ammonia first. This ammonia has a lone pair of electron like this. So let us draw the electronic configuration of nitrogen first. What is the atomic number of nitrogen? It is 7. So you can write 1s2, 2s2, 2p, 2, 4, 3. Right? So totally 7. And the outermost has 5 electrons. It means you can draw by the box model 1s2, 2s2, 2p, 3. 1, 2, 3. Right? And what about this outermost shell? The second shell is the outermost shell. It contains one. This is called lone pair of electrons or non-bonding electrons. Lone pair of electrons or non-bonding electrons or unshared pair of electrons. Okay, you must understand all these terms. All are same only. What are those called? Lone pair of electrons. Tell me. Hmm.
Lone pair of electrons, non-bonding electrons, unshared pair of electrons.
In the மூணுமே ஒண்ணுதான். Okay, right. And what about these? They are called bonding electrons. So they are known as bonding electrons. B means bonding electrons. Suppose when I draw the structure of nitrogen, I mean ammonia. So ammonia now it has got one electron, another one electron, another one electron, and this is non-bonding. It is not involved in bonding. That is why it is called non-bonding. They are kept alone, and that is why it's called lone pair of electrons. So this is represented by a pair of electron, and this is also represented by this. Okay, so lone pair of electrons. And the bonding is developed between nitrogen and hydrogen with the three bonds. Hydrogen has got one electron, nitrogen has got one electron, hydrogen has one electron. So they develop a bond. Okay, and what about hydrogen here? What about another hydrogen here? Okay, so this is the sp3 hybridized one. It involves S and the P, is it not? And there is a lone pair of electrons, and that is why it has got the tetrahedral structure like this. Actually, this is trigonal. It looks like a camera tripod. So H, and this hydrogen is above the plane of the paper, and one hydrogen is on other side. So a pair of electron is located like this. So this is the structure of ammonia. And why it is called a nucleophile? Because it has got the lone pair of electron. So it has got the electron richness. So this is electron enriched molecule, neutral molecule. Even though it is not negative, but they can act as what? A nucleophile, because it has got electron, lone pair of electron, non-bonding electron. So with this, they can approach the positive center. Is it clear now? So this is the structure of ammonia, and that acts as nucleophile. Now let us move to the another one. And how it is present in ammonia, let me consider. We will replace one hydrogen by methyl group. Then it is called amine. So the same nitrogen, and here one hydrogen and another hydrogen, and one hydrogen is replaced by methyl group. Okay, then it's called, and there is a lone pair of electrons still. So this is amine, and this can be simply represented as CH3NH2, and there is a lone pair. And this one is ammonia NH3, a lone pair. Okay, and let me further expand it. We'll try to replace another hydrogen by methyl group. Then it is called dimethylamine. And what about this? This is called primary amine. Primary amine means it has got only one methyl group, one alkyl group. So methylamine. And let us consider the same nitrogen, bond, and there is a lone pair. So here one methyl group and another methyl group. Now hydrogen. So what do you call this? This is secondary amine. It means CH3 twice and NH. Still you have a lone pair. Okay, draw. And this is known as dimethylamine. Dimethylamine. Now let us have another structure, that is N. Replace another hydrogen with CH3. So CH3. So this hydrogen is further replaced by CH3, one more CH3. So this is CH3 thrice and N, and there is no hydrogen. But remember, still you have lone pair of electrons. Are you able to follow? And what do you call it? This is tertiary amine. That is trimethylamine. And then you have another group. Let me replace further. You have nitrogen. You have got already what? This CH3, CH3, CH3. Now this is the lone pair of electrons. And one more CH3, Cl, methyl chloride, is coming towards this ammonia. So in that case, what will happen? This bond, this non-bonding electron is donated to the incoming methyl group, and thereby NCH3 CH3, CH3. The fourth one is permitted, but it is donated. And it has lost by that because both the electrons is donated to form a bond. So it becomes what? Plus, and this is Cl minus. So this becomes an ionic compound that is called tertiary, not tertiary, quaternary ammonium, quaternary, that is salt, ammonium salt. Ammonium. Why it's ammonium? Because it has attained a plus. So ammonium and it is a salt. So quaternary ammonium salt. That is tetraalkyl amine or tetraalkyl ammonium chloride. So here it has lost its what? The lone pair by donating its lone pair, non-bonding pair to the incoming methyl group, and thereby it is known as quaternary ammonium salt, quas. And it is a very good solubilizer. In fact, you can convert the organic compounds, which are all generally polar, I mean non-polar compounds. By introducing this, you can convert it into a polar one. So thereby we can, and that is why they are called solubilizers. That is, it can make it compatible with polar solvents. Okay, is it clear? So I have detailed, that is ammonia, then amine and amine of different types also. Now let us talk about water, the structure of water. See, oxygen, what is the electronic configuration? Atomic number 8. So 1s2, 2s2, 2p2, 2p4, because totally 8. So let us introduce the box model 1s2, 2s2, and then 2p4. 1, 2, 3, 4. Right? And what about hydrogen? It has got only 1s1. Okay. Now you have 6 electrons. 4 plus 2, 6 electrons in the outermost shell. And that should be bound with the what? Water molecule. So one hydrogen can be accommodated here. Another hydrogen can be accommodated here. But what about the leftover? There are 2 unpaired electrons. Do you understand this? They do not involve in bonding. So these two, that is this one. Let me write the water molecule structure. So here you have got, I am writing only the outermost shell. So 2s2 is there. And you have 3 shells, 1, 2, and 1, 1. Is it not? Now, what happens? That is, this is from hydrogen. This is from another hydrogen. Are you able to follow? So this is from one hydrogen and this is from another hydrogen. And thereby it makes a bond. But what about this? This 2p, 2s2 and 2p2. These two are left over. They are non-bonding electrons. That is lone pair of electrons. Okay, and that is why it is represented by 2 pairs of electron. So this oxygen, in the case of water, it is drawn like this. So this is the oxygen. You have got, okay, now this is the 2 lone pairs, and you have got 1 electron, another electron. Now this is from hydrogen. You can make use of different colors so that you can understand the concept very clearly. Okay, so this involves in OH bond, this involves in another OH bond, so that you have got 2 lone pairs of electron. but actually it is positioned nearby. So let me draw once again. It won't be looking like linear like this. So let me assume this is oxygen. The lone pair can be represented in this way, and this is another lone pair. Okay. Now you got H here and H. Okay. Now because of the lone pair, they repel each other. So there is a repulsion between lone pair and lone pair, and this repulsion again repel the hydrogen. So it pushes the OH bond, and this is a bonded pair, is it not? So what about this? This is bonded pair. This is also bonded pair. So there is a repulsion between bonded pair and the lone pair, and that results the oxygen, water, to have a bent structure, a V-shaped structure like this because of the repulsion. So it comes down. And what about this? They want to keep away from each other. So you can put like this. As you know, like charges, that is same charges, they repel each other, is it not? And that is why they repel. So you are able to get the bent structure, that is V-shaped structure, bent structure of water. So this is the correct structure, whereas this is the linear structure. This is ruled out. So from linear to it has become bent structure. Okay. Then now this concept is known as Vesper theory. Take down valency shell electron pair repulsion theory. So Vesper theory means what? That is valency shell electron pair repulsion theory. Do you understand this? So VSEPR, Vesper. Valence shell means that this is bonded pair. And so, what are the types of repulsions taking place? These repulsions may be of, that is, lone pair versus lone pair, bonded pair versus bonded pair, and lone pair versus lone bonded pair. Among these, lone pair versus lone pair will be the highest. Okay. So this is regarding. So in fact, this is regarding a Vesper theory. In fact, this Vesper theory helps to understand the different types of structures it developed. And then now I think I have completed the water. That is oxygen present in water. Similarly, hydroxyl group means alcohol. So let us consider ROH. How to draw the structure? You've got already two pairs. For oxygen, it is 6, 2, 4, and here 5, 6. That's all. Okay. So this is alcohol. It can be expanded like this: CH3 alkyl group, O, and then H. Okay. Then what about ether? Ether is ROR. This is called ether. Okay. This is called ether. Then, and I was talking about the, so these are all also nucleophiles. Then what about the sulfur? Sulfur, it has got two lone pairs. As in the case of RSH, instead of ROH, you can put RSH. So you got one lone pair, another lone pair. Okay. So this is known as thio alcohol, that is thiol. I hope now you are very clear about the nucleophile of neutral molecule type with electron richness. So they have unshared pair of electrons. Okay. Now let us go to the negatively charged entities like halides, hydroxyl group, alkoxyl group, carboxylate group. Let us discuss the structures of these compounds, I mean reagents. X means halogen, X minus means halide. For example, you have chloride, bromide, iodide, etc. And what about let me explain about at least chlorine. What is the atomic mass of chlorine? Anyone?
35.
That is atomic mass. Atomic number
70.
17. Okay. Atomic number is 17. So 1s2, 2s2, 2p6, 3s2, 3p6. Now you just count 2 and then 4, 10, 12, it becomes 18. So reduce 1. So what is the outermost shell? 3s2, 3p5 only. So let us draw the 3s2 and the 3p5 boxes. So this is 3s2, 3p5. So 1, 2, 1, 2, 3, 4, 5. Okay. So the chlorine, valency is nothing but the number of electrons available in the outermost shell. So can you say, sir, you got 7 electrons and that is why the valency of chlorine is 7? No. In this case, instead of losing all these 7 electrons, the chlorine can easily withdraw 1 electron and thereby attain the octet stability. Okay. And that is why the Cl becomes Cl minus quickly. Now it becomes what? 3s2 and then 3p6. How they attain 3p6? 1, 2, 3, 4, 5. Then probably it would have withdrawn some electron from other reagent. Okay. And that is why it becomes Cl minus. So now it is enriched with this one. So becomes, it has got one more electron. So it becomes Cl minus. Thereby it becomes a nucleophile. So this is negative. So the negative entity can go in search of a positive carbon ion, that is cation. Okay, that is why chlorides, bromides, iodides are also, that is negatively charged atoms are called, reagents are called nucleophiles. Okay, similarly OH minus nucleophile, alkoxide mean or O minus. You've got alcohol ROH. When you remove one hydrogen as H plus, then definitely it becomes RO minus. So this is called alkoxide. Okay, it is derived from alcohol by removing one proton. So it becomes RO minus, alkoxide. You can put alkoxide, K, alkoxide. Okay, you can put K here. ALKOXIDE, alkoxide. And you have similarly carboxylate. Carboxylate means or COO minus. Carboxylate. So carboxylate, we can draw the structure of carboxylate. This is called a carboxylic acid or COOH. Carboxylic acid. Now see, you can draw double bond O R and this is O then H. This is the way you have to write down. And carboxylate means one hydrogen is removed as H plus. So it becomes minus. This electron is possessed by this. So it becomes R C double bond O O minus. I can show this by electrons also. Electron dot. So how to show the electron dot here? You got on what is the valency of oxygen? I mean the number of electrons available in the oxygen. 6, is it not? So you can put 2, 4, 6. And here you have got 2, 4, right? And then you have another set, then there is an excess of one electron here. And that is why it becomes what? Now here 2, 4. In this case, 2, 4, 6 plus 1, 7 it has become. Okay. So you can count the electrons also like this. How many electrons are there in oxygen here? 2, 4, 6. 6 electron. Here 2, 4, 5, 6. 6 electron. And what about this? 2, 4, 6 electron. And here 2, 4, 6 plus 1, 7. That is why it becomes minus. Do you understand this? Because oxygen, this oxygen has got one more electron. So you should be aware of the electron dot formula also. That will be very helpful for you to understand the mechanism very clearly. Okay. Now let us talk about the electrophiles. Electrophiles. Electrophiles means what? They are the positively charged entities that they go towards the negative center, that is corb anion, just opposite. So they are positive, or that is electron deficient group, approaching carbocation. I'm sorry, carb anion, C minus. File means to attract electron. So they go towards the electron rich center. So it's carb anion. Okay, please correct this, carb anion. Now let us have the two types. One is the positively charged electrophiles. Another is neutral electrophiles. Neutral electrophiles with electron deficiency. Electron deficient. Of course, no charge is involved, but there will be some electron gap, you can say, electron deficiency. Here, carbocation itself, R plus. Example, proton is also electrophile. Alkyl halide, RX you can put. Alkyl halide, or X. And actually this is a neutral one, so you can put here RX. Otherwise you can show like this. For example, this is RX only, but you can simply put X plus. Okay, X plus. And here O plus, oxonium. Similarly, nitronium, NO2 plus. So these are all electrophiles. They are positively charged. And neutral electrophiles are carbon dioxide, CO2, then dichlorocarbene, CCl2. Okay, this is called dichlorocarbene. So we have thoroughly studied the what neutrophiles, I mean nucleophiles, then electrophiles, and we have seen various examples also. Now let us discuss how the electrons are moving in an organic reaction. How we can represent the electron movement in organic reactions. Data. Electron movement in organic reactions. Type 1. Type 2, type 3. Let us illustrate type 1. This is called a lone pair to bonding pair. Lone pair to bonding pair. Type 2 is bonding pair to lone pair. Type 3 is bonding pair to another bonding pair. That's all. Now let me illustrate. So here you have a hydroxyl group like this, OH. Hydroxyl group, you should be aware of the electron dot also. So oxygen, this is OH minus. So it can be put minus. OH minus means 7 electrons. 2, 4, 6 plus 1, 7. Right? And there is a proton approaching here, positive in type T. So definitely, how you can predict the movement? This is having excess of electron. So this pair of electron, that is, this is lone pair. Okay. So this lone pair may approach here. Okay. To form a bond H O H. Now it has lost one pair, so it becomes like this. Okay. It is a very simple example. Now you can understand that this is the lone pair, is it not? What about this? A lone pair has become a bonded pair. Do you understand this? And that is why I said lone pair to bonded pair. Okay. Now let me consider formaldehyde, HCHO. Okay. HCHO. It has got so 2, 4, 6. Now the bond can move here. Okay. Got it? So that it becomes O and excess pair is moved here. So it becomes minus. Okay. Then it becomes CH2. This carbon has lost one electron, so it becomes plus. Do you understand this? Okay. And another type, that is bonded pair to bonded pair. Let me consider. Can you guess what this molecule is? Anyone? This is an alkene, double bonded killer. And how many carbon atoms are there? 1, 2, 3. So propane. So this is the propane with the positive ion. So this CH2 plus is a positive ion, and probably this is the bonded pair already. So one bonded pair to another bonded pair, it can move like this. So that it becomes what? CH2. Now here also you got CH2, okay? And you can, if you want, you can put CH2 here. What about this? This is simply CH only, okay? Now this CH2 has attained plus charge because it has lost one pair, and CH, then CH2, and now it comes here. Are you able to understand? So this is bonded pair, this is another bonded pair. So bonded pair to bonded pair, it is shifted. So likewise, you can have three types of what? Electron movement in organic reactions. So we'll have a short break. After that, we'll be discussing about the electron displacement effects in covalence bonds, where we'll be discussing about the very important concept, inductive effect, inductomeric effect or electromeric effect, mesomeric effect, then hyperconjugation, the resonance. All these things are brought under one concept here. Is a very, very important. Once you are able to understand thoroughly, it would be very easy for you to solve any organic reaction based problems. Okay. Any doubt?